All welcome to this PowerPoint presentation. This is Group 27 and we are presenting on Metal Organic Frameworks, MOFs. So under this topic, we'll be looking at the structural characteristics of metal organic frameworks, synthesis of metal organic frameworks, applications, challenges and future outlooks. So, introduction to MOFs. Metal organic frameworks, that is MOFs, are a class of porous crystalline materials composed of metal ions or clusters connected by organic linker molecules. They are a versatile and rapidly evolving field in material science, offering unique properties and applications. More formally, a metal organic framework is a potentially porous extended structure made from metal ions and organic linkers. An extended structure is a structure whose subunits occur in a constant ratio and are arranged in a repeating pattern. Structural characteristics of MOFs. 1. Tunable porosity. MOFs can be engineered to have customizable pore size and volumes, allowing for targeted applications like gas storage and separation. 2. Diverse topologies. The combination of metal ions and organic linkers can result in an extensive range of intricate 3D network structures. 3. High surface area. MOFs often exhibit extremely high specific surface areas, making them ideal candidates for catalysis, adsorption, and sensing. Synthesis of MOFs. Formally, MOFs are created by mildly mixing metal ions with organic linkers to create porous and crystalline materials. During the last couple of decades, different preparation schemes have evolved and been applied to prepare MOFs. They include 1. Solvothermal synthesis, 2. Microwave assisted synthesis, and 3. Mechanochemical synthesis. Solvothermal synthesis. It involves dissolving metal salts and organic linkers in a solvent and heating the mixture in a sealed vessel called autoclave at high temperatures, typically from 100 to 250 degrees Celsius, for several hours to days. Advantages: it produces high quality crystals, allows for control over crystal size and morphology. Disadvantages: it requires high temperatures and long reaction times, not always environmentally friendly due to solvent use. Microwave assisted synthesis. It uses microwave radiations to rapidly heat the reactants, reducing synthesis time from hours or days to minutes. Advantages: it has faster reaction times, energy efficient, and can produce high quality MOFs. Disadvantages: limited scalability, requires specialized equipment. Mechanochemical synthesis involves the grinding the metal salts and organic linker together, often without solvents, using a ball mill or mortar and pestle. Advantages: it's environmentally friendly, that is, there is no solvents, simple and quick and scalable. Disadvantages: may produce lower crystallinity MOFs, difficult to control product morphology. The application of metal organic frameworks. 1. Gas storage. MOFs can store gases like hydrogen, methane, and carbon dioxide efficiently due to their high surface area and porosity. 2. Catalysis. MOFs can serve as catalysts for chemical reactions, offering advantages like selectivity and reusability. Separation. MOFs can separate molecules based on size, shape, or chemical properties, useful in industrial and environmental processes. And 4. Drug delivery. Metal organic frameworks can encapsulate drugs and release them in a controlled manner, making them potential candidates for medical applications. 1. Gas storage. Specific examples of gas stored are hydrogen, methane, and carbon dioxide. Advantages of gas storage over other storage methods. It has higher storage capacities, lower pressures, and safer storage conditions. Potential application in energy and environment. Hydrogen storage for fuel cells, carbon capture and storage CCS to mitigate climate change. Catalysis. Mechanism of catalysis in MOFs. MOFs can provide active sites for reactions within their porous structure. Example of catalytic reactions are oxidation, reduction, and polymerization reactions. The industrial relevance. Metal organic frameworks can be used in chemical manufacturing, environmental remediation, and energy production. Separation process in metal organic frameworks. Types of separations. Metal organic frameworks can separate molecules based on size exclusion, that is, the molecular sieving, shape selectivity, and chemical affinity. Examples of industrial processes are the purification of gases, for example, separating oxygen from nitrogen, separation of hydrocarbons, example, separating xylene isomers, and the removal of contaminants from water, for example, heavy metal ions. Environmental applications. Metal organic frameworks can be used to clean up pollutants, recover valuable resources from waste streams, and purify drinking water. Drug delivery. 1. Biocompatibility. MOFs can be designed to be safe for use in the human body. Mechanism of drug encapsulation and release. Drugs can be encapsulated within the MOF structure and released in response to specific triggers. Examples of drugs and medical applications. Delivery of anti-cancer drugs, antibiotics, and controlled release of therapeutics. So the challenges in metal organic frameworks synthesis. There are various challenges faced in the metal organic framework below. Below are some of the challenges. 1. Synthesis challenges. 2. Stability challenges. 3. Scalability challenges. And 4. Economic challenges. So we go through them one by one after the other. So one, synthesis challenges. Under synthesis challenges, there is consistency and producibility. One, batch to batch variability. Ensuring consistent and quality and properties across different batches of MOFs can be difficult due to variations in synthesis conditions. Producing results from different research groups or scaling lab scale synthesis to industrial levels while maintaining the same material property is challenging. Two, time and energy consumption. Long synthesis time. Some of the metal organic framework synthesis methods, such as solvothermal and hydrothermal, require prolonged reaction times, which can be impractical for large scale production. High energy cost. Methods like solvothermal synthesis often require higher temperatures, leading to increased energy consumption. Stability challenges. Environmental stability. Under environmental stability, thermal stability, some of the MOFs decompose at relatively low temperatures, limiting their use in high temperature applications. Chemical stability. Many MOFs are sensitive to moisture, acidic or basic environments, which can lead to degradation of the framework. Mechanical stability. MOFs can be brittle and may collapse under mechanical stress or during activation process. Scalability challenges. One, large scale production. Under large scale production, we have material cost. The cost of materials, including metal salts and organic linkers, can be high, making large scale production expensive. Process optimization. Scaling up from laboratory to industrial scale production requires optimization of synthesis processes to maintain efficiency and quality. Two, environmental impacts. Under environmental impacts, we have the solvent use. Many metal organic framework synthesis methods rely on large volumes of organic solvents, posing environmental and safety concerns. Waste management. Managing and disposing of waste products generated by metal organic framework synthesis is a significant challenge. Economic challenges. One, cost effectiveness. Under cost effectiveness, we have raw material cost and the manufacturing cost. Under raw material cost, the high cost of metal precursors and organic linkers can make manufacturing can make MOF production expensive. Manufacturing cost. Developing cost-effective manufacturing processes that can produce MOFs at a competitive price point is challenging. Two, market adoption. Under market adoption, we have the performance versus cost and regulatory approval. Most MOFs must offer significant performance advantages over existing materials to justify their higher costs and gain market acceptance. For application in healthcare or food industries, MOFs must undergo rigorous testing and obtain regulatory approval, which can be time consuming and costly. The future outlooks in the metal organic framework synthesis. One, green chemistry approaches. developing environmentally friendly synthesis methods that reuse renewable resources, reduces energy consumption, and minimize waste. 2. High throughput screening, utilizing automated systems to rapidly synthesize and screen a large number of metal organics framework candidates for desired properties. 3. Post-synthetic modifications, applying chemical modification to MOFs after their initial synthesis to introduce new functionalities or enhance existing properties. Metal organic frameworks represent a groundbreaking class of materials in vast potential across applications, including gas storage, catalysis, catalysis, separation processes, and drug delivery. Their unique combination of high surface area, tunable porosity, and versatile functionality positions them as key players in addressing some of today's most pressing scientific and technological challenges. Continued research and innovation are essential to overcome these obstacles, enhance the performance and practicality of MOFs, and unlock their full potential. The future of MOFs is promising, with opportunities from new applications and advancements that could revolutionize various industries. Thank you.